Good afternoon, everyone. Sorry, I was having a hard time connecting. Plus, there were like 14 updates that had to be done before I could get there. So I'm sorry. Okay. Yeah. Okay, remember, go ahead and sign in. Thank you. It's in the chat. Yep. All righty. Perfect. Thank you. All right, let me see if I'm ready to share my screen because I had so many updates. I don't think I ever got to it. Nope, not yet. I haven't. Okay. Unless, oh, it's coming. It's loading right now. There we go. It's loaded. Mhm. All righty. Here we go. Modules. And let's go to where we are. We are looking at matter. All right. So matter states and properties. Let's see. Okay, yeah, we're going to look at kinetic molecular theory of matter. That's what we're going to look at next. That's a bonus. That's a one. Sorry, got the wrong one on there. I want the diagram. Stop doing that. What are you doing? There we go. What are you doing, kitty cat? All right. Oh, there's somebody else. Let me download that. I'm downloading this to see it more. Okay, there we go. Now we can look at it and I can share. And don't forget to sign in. Those of you just came in. Okay, sharing screen. All right, so you should be able to see this kinetic molecular theory of matter diagram that I have here, right? Okay, so let me make it bigger. So basically, all this is showing you how the kinetic molecular theory of matter works. If you have a solid, usually your atoms or molecules are very close together and they're in fixed positions, and all they can actually do is vibrate. So a solid requires more intermolecular forces because they are much closer together. So to be kept together, they have to be attracted to each other, right? That makes sense. And as you know, if you just picture ice melting like what we did in the lab, solid was very cold, right? So that's the lowest temperature. As you are moving into the melting phase, you are going to become a liquid eventually. And once you become a liquid, your molecules or atoms are more loosely arranged. And basically they have enough space that they can actually slide past each other. That's why water pours a certain way. But their intermolecular forces are still there. They're not as high as in a solid, but they're still present. And the intermolecular forces hold those molecules of water together so that when you pour, it's all one stream. Then you have the next part, which is the kinetic energy. But as you know, temperature is the measure of the kinetic energy, the average kinetic energy in a system. And so the temperature and the kinetic energy go together, right? So as temperature increases, so does the kinetic energy. They move more. So therefore, they have more space to move. You see, so it all makes sense if you put it together. When you have a liquid and you keep heating it, then you have what is known as evaporation, right? And it turns into a gas. When you get into the gas phase, the temperature is at its highest. The kinetic energy is also at its highest. The distance between the molecules is at the greatest of all because they're very far apart from each other, but the intermolecular forces are non-existent or almost not non-existent because they can't be attracted to each other if they're far away. That kind of makes sense too. All right, so as you are increasing everything, the temperature is increasing. The molecule move more and the distance is greater. All of that makes sense. And then the intermolecular forces go the opposite way. So now, when you have a solid, you have a definite shape, right? And a definite volume. We said that. And in a liquid, you have a definite volume because you can still measure the volume, but you don't have a definite shape because the molecules will take up the shape of the container. And when you are becoming a gas, you don't have either a definite volume or a definite shape. Now, when you move the other way, obviously, when you become from a gas to a liquid, you're going to be losing energy because you have to actually put it out of your system. And so where it goes is into the environment. Before the solid absorbs the energy from its environment, right? But now it's releasing it. The gas is releasing it so that it can condense, and then it slows down. And since it slows down, the molecules become closer together. Therefore, the intermolecular forces come back. And as you freeze, the molecules become rigid, so in fixed positions, and the intermolecular forces increase even more. And the temperature, of course, drops because the motion stops. Well, not really stops, because motion, everything is always in motion. Every single atom is always in motion, even if it's just vibration, but it's still in motion. That's motion. Okay, so now there is another term that we didn't go over, and that is when a solid becomes a gas directly, does not go through the liquid state. Think of dry ice. When you have dry ice, it smokes, right? Is what people think. It's smoking, but it's evaporating. And the reason it's doing that, it's because it is going to lose that energy very quickly, and it won't have time to become a liquid. So it becomes a gas immediately. And that is, the term for that is sublimation. And then the opposite term, when it becomes a gas, when it's a gas becoming a solid directly, as in when you have in the morning, you wake up and there's dew formed on the ground, that is known as deposition, or frost, excuse me, not dew. I meant frost, frozen dew. So frost, that is deposition. Basically what happens is the temperature drops quite fast, and instead of going through the liquid state, it becomes a solid immediately, and that's the vapor in the air. So that's why you have frost, and that's what deposition is. Okay, so this diagram kind of helps you understand that by looking at it a certain way. All right, okay. So now let's go into more stuff. And let me get this out of the way. All right, so we were looking at kinetic molecular theory, but we really need to look at more of this. Okay, so you know the phases, we already talked about that. Phase changes, we talked about that also. But the one thing we haven't really covered, and sorry, I'm gotta find this stuff as I'm talking, you just gotta stop talking for a minute, is how to separate them, an actual mixture. This is very important right now. We have got to understand this because we have an essay question that you have a rubric for that you're going to have to actually do. So how do we separate a mixture? Well, since it is a mixture, right, we are going to separate it using only physical means. We cannot use chemical means for a mixture. Mixtures are not compounds. Compounds do need chemical separation, but mixtures don't. Okay, we are separating several compounds or several elements or whatever, or a mixture of compounds and elements. We don't know yet because we haven't seen this yet, but we are definitely going to be separating things. And there are certain things that I'm going to show you that the separation will depend on. And then you have to come up with your own procedure to separate the stuff that I was telling you. Okay, so in this case, we're going to look at some mixtures and solutions. So we're just to recap, a pure substance contains only one type of particle, but a mixture contains at least two different types of particles. And by particles, we mean either atoms or molecules. A liquid can be pure or it can be a mixture, right? We can have pure water or we can have mineral water, for example. All right, so in this case, I just gave you one of these, but which of these are mixtures?
Coffee.
Coffee, yes, definitely. What about orange juice?
Yes.
Yeah, so that means all of these are mixtures, right? Because they contain more than one type of particle, right? That's why what we know. I know mineral, see, mineral is telling you there's something in the water, right? Orange juice, you know, just by drinking it, that there's stuff in there, like sugar, and there's vitamin C, and, you know, all of these are different compounds that are in there. And there's water also. And then coffee, of course, has just water and also coffee. So there you go. So when you have a mixture, you have, most of the time, you could have a solid and a liquid, and there's a thought about this. Does the liquid dissolve? The answer is yes. Then what you will see is the solid is no longer visible, like when you put salt in water. And the solid that dissolves in water is known as a soluble solid. If it doesn't dissolve, then you will still see the solid. There may or may not be a color change with the liquid, because with the soluble one, but not with the insoluble one, because if nothing is actually incorporating into the solution, dissolving, then there's nothing that needs to be given off. But whereas when it dissolves, let's think of Kool-Aid. You're putting Kool-Aid in, it was water, now it's red or pink or whatever color Kool-Aid you put in there, right? Because it was soluble. But if the Kool-Aid had been insoluble, the Kool-Aid would have stayed as a powder below and no color change would have happened, right? Okay, so that's what this is talking about. All right, so this is some terms that we need to know. All right, so a solution, we know what it is, but there's other things that we need to know about a solution. When you put something into something, the something that you're putting it in, right? The liquid that you're putting it in is known as the solvent, okay? That is what does the dissolving. The solute is the substance that you're dissolving. So when you dissolve it, and it becomes a solution, okay? So that's the 3 S's of solubility. So you got a solvent, got a solute, and you got a solution. All right, so next thing is our separation techniques are going to be based on certain things. Okay, so let's think about this. How do you separate pasta from cooking water? What do you use? How do you do it? Most people would say use a strainer, right? Or a strainer. Okay. So how are you keeping tea leaves out of a cup of tea? Well, usually they're in a baggie, right? Okay. So they're encased in something. And how do you keep coffee from a fresh pot of coffee? When you make it, you have to use a filter. That is all of these techniques. Believe it or not, the actual word for this is filtration. Okay. So any insoluble particle, that means the ones that don't dissolve, can be separated from a liquid by filtration. Or if you want to use the verb, filtering. Okay. So we're skipping this stuff. We don't want to do that. But here's an actual thing that, okay, so you if you look at the sea, you know that is a big mixture. It's got fish, it's got salt, it's got boats, it's got all kinds of stuff in there. So it's easy to separate that. But the smaller stuff, the soluble stuff, is harder to separate. And that's the salt. And how do we do that? Okay, so when you do a separation like this, what you have to do is you have to evaporate the liquid by you remove it by evaporation. You can't just filter it because they're both dissolved. So, one of them is dissolved in the other, so they're both about the same size, so you can't filter. So what you do is you remove it by evaporation. And how does this work? Well, the liquid and the solid both have different boiling points. Okay, and evaporation happens at different times. Therefore, you can evaporate the liquid, but the solid will remain. All right, so remember we said that the heat comes from the surroundings when you're doing this. If you're heating something, you are transferring heat from something that's already hot into something that's not. So it absorbs it, okay? So before you evaporated it, and this is after, and it's not this neat, but yes, it's similar. All right, so we are going to next figure out. Okay, so this is one of the actual applications of this. It's called solution mining. Basically, what they do is they pump water into well, they dig a hole first, then they pump the water in, and the salt is in there, and it dissolves. Then they pump it back out, and they do the evaporation on there. So you got the solution and the evaporation happening. And then, of course, the impurities are removed in the water. And then you have salt. Okay, so that's how it works. Now, there's another technique known as chromatography, and this is a chromatogram. What you are going to do is you're going to basically, and this is something that's missing here because my permissions that I used to have don't work anymore, so I'm going to do it manually. All right, so basically what you would do is you would take a black ink, let's say, well, not black in this case, more like yellow ink in this case, and you would put a drop of it here, right? Okay, so come on, give me a drop right here. Boom. It's not letting me. It's there, somewhere there. Okay, and then you would take one of red ink and you would put it here. That's kind of like your controls, right? Okay, let's just say that. Come on, why aren't you letting me put it? There we go. That's what I want to do. All right, and then the other one would be orange, because you know orange is a mixture of yellow and red. So then your other orange would be there. Then you would place this in water. Water would be drawing up, right? This water would be coming, oops, let me do that in blue so it doesn't look so weird. Okay, so let's do blue. Okay, so the water would be getting up the paper, and as it does, it dissolves this right here, it dissolves this right here, and it dissolves this right here, right? And as you bringing it up, right, it stops at a certain point. And the reason it stops is because the mass of the things is either more or less. So if you think about it, if you're carrying a stone that is heavy, you're going to carry it less distance than if you're carrying a stone that is not so heavy, right? Because eventually your arms are going to get tired or whatever. Well, same thing here, except it's a little different. Obviously, this has to do with getting the mass that it's no longer being dissolved in it, I guess you could say. So it drops off because it's heavy. So it drops off first. So in this case, and it actually goes here to here, obviously. Okay, so when you are having just a pure substance, see, it just rises as much as it can, and then it drops off. The red one is a little lighter, so it goes higher. And the orange, though, that contains both, separates. You see that? And this is known as chromatography. It is very similar in principle, okay, to the DNA separation. I don't know if you remember that. You've ever seen a DNA thing? It has rings. I mean, it has like bands. Okay, well, those bands that are forming, like, you know, you have a band there, a band there, a band there, and a band way up here, whatever it is, they identify the DNA. Okay, well, it's a similar process. Then they do also go by mass. All right, I said wait, but it should be mass. The mass of this one is much lighter right here than the mass of this one, right? Because this one got dropped off first. And in this case, instead of it being carried by water, by solution, because DNA is not soluble, it's being carried by electricity. So they put a current through, which carries, because they're charged, carries the bands up the gel. So that's kind of how that works. All right, anyway, let's clear that. All right, so that's what's going on here. And that's what is known as chromatography. That's one way of separating something. And we can do that as an experiment over at school. I'll bring some coffee filters and you'll like this. All right, but obviously the markers that we use have to be water soluble. If not, we're going to have to use alcohol, right? Because, and we'll do both actually. We'll do a marker, you know, that is supposedly going to move with alcohol and one that will not move with water. Just so that you can see the difference. It has to be soluble in it, otherwise it doesn't move. All right, so the next thing that we're looking at is the next separation technique, which is known as distillation. We cannot do this. Well, we do have not a distillation apparatus in there, but basically it is composed of three parts. You have the boiling area, the condensing area, and the collection area. Okay, so those are the three steps that you have. Okay, now, if you think about it, the hot gas that's coming in as the water or the liquid that we want to separate evaporates is coming into the top of the thing. So if we put the water out here, then the condensing would take a lot longer, or it actually may not even happen because you're letting the water out over here on the bottom. So instead, you have to put the water in the bottom so that it flows up and then it comes out when it's hot. You see, makes sense, right? Okay. And the liquid that condenses is collected at the bottom, and you notice it's at an angle so that gravity just takes care of that. All right, so there are the two things that you want to know. Okay, so the choice of separation technique depends on two things. Is the solid soluble or insoluble? So that's your first thought. If it's insoluble, then you know you can filter it out. If it's soluble, then you know you're going to have to either use chromatography, you're going to use distillation, or you can use evaporation. Depends on what it is, right? And the other thing, do you want to collect the solid or do you want to collect the liquid? Well, we don't want to collect the liquid because that's going to be our adding thing. So we are actually going to use evaporation. Okay, that makes sense. All right, so let's keep going. All right, so now we have a matching thing, and I want you guys to put in on the chat how you would match it. 1A, 2B, you know, whatever. Just put it on there, how you would match it based on what you know now. And then I'll give you the answers. But go ahead and put it in. Just write it in the chat. Okay. Just looking. All right. Nobody's answered yet. You've got to read a lot, I know. Okay. Yeah. Okay. So no answers yet. All right. Well, since you're not answering, let's look. Okay. So which one would you use if you have an insoluble solid, like this one right here? See, there's the keyword, insoluble. Hold on, let me go in here. Insoluble, see, solid. Okay, that is filtration, right? So that and that go together. Okay. Now, the next one is small amounts of two or more solids which are soluble in the same solvent. Okay, we only did this one with chromatography. So that would be you, right? And then, and this is a question on your test, by the way, so better pay attention. Evaporation. Do we care about the liquid in this one? No, we only care about the solid. So obtain the solute. See, that was the word. Remember the solute. So that's that one. And by default, this one has to be distillation, right? Because we want the solvent. Okay, so there you go. That's your matching. All right, let's clear that. And now let's go to a question that we could have, that we could answer. Okay, hold on. I don't know why. Oh, I know why. It's because I don't have a mouse. It was not letting me. There we go. Okay, so now what I'm going to do is I'm going to go back to a place where I have, I'm probably going to stop sharing. Yeah, good. I did stop sharing. Good. That's what I wanted. Because what I want to do is I want to go get the one that I use usually for explaining to you how to separate a mixture. Get that ready, but let me go get the actual file that I need. Separation of a mixture. Okay, I just want it on documents. Okay, again, separation of a mixture. It's not coming. It's coming. It's just got to find it first. Okay, here we go. Okay, so this one, okay, yeah. All right, now I can share my screen again. Okay, let's go back to it. And let me share my screen real quick. And here's what you would be doing. Okay, so this is, see how it's telling you it's the purpose is to carry out a separation of a mixture. And the mixture that you have is not here. I thought I did have the mixture, but I don't have it. Hold on, I gotta find the rest of it. The mixture, let's see, that's the lab part. So that's where the, hold on. There's another one, mixture separation. Yeah, oh, that's still the same one, darn it. Where is it? Anyway, so let's just say, I'm gonna type it in just to say something. Okay, so let's say we have, this is our mixture. We have iron filings. We have poppy seeds. We have salt. We have, let me think, what else can I put in here? Let's say another type of seed, coriander seeds. Okay, let's say we have this, okay? Let's see, that's 1, 2, 3, 4. I need one more. There's usually 5 things. Let's just do 4. Okay, can't think of anything else right now. Sorry. Oh, let's say we have some pieces, some copper pieces. Okay, how's that? There we go. All right, so that's what we have. All right, so the first thing we need to do is we need to figure out what our things do. First, iron. We know iron. Iron is what is known as a magnetic metal because it is part of what is known as the iron triad. The iron triad is the three elements that are next to each other. Iron. Then the next one would be nickel. Oh, sorry, cobalt and nickel. So that's the iron triad. So these are the ones: iron, cobalt, and nickel. That is known as the iron triad. So iron is one of them, right? Copper is not. So we could use a magnet. See, and that's up here. The equipment on there is in your thing, and it tells you what to do. So that's the first one. Poppy seeds. Poppy seeds are teeny tiny. If I actually drew a picture of one, I think I would just do, no, that's a little too small, maybe like that. No, that's way too big. See, that's more or less kind of what a poppy seeds look like. Salt, you know, coriander seeds are more like about yay big, right? And copper pieces were just little chunks of copper, like we've cut, we've cut up. Okay, so all right, so you notice how they're increasing. Now, are poppy seeds gonna be soluble? The answer is no. Is coriander seeds? No. Copper? No. Iron? No. So none of these are soluble. So we first got to separate all of these out of there before we can even deal with the salt. Okay. So first we said iron, we were going to use a magnet. So we got that one. All right. Now, the one thing we know is that coriander seeds are large. So if we use a sieve, right, that has holes that are a little bit big, we could separate both the copper pieces and the coriander seeds out of there. All right. The copper pieces are a little bit bigger, so let's say more like that. Okay, so let's say we do this and these go through the sieve. So, but this one is separated. Okay, so now we have poppy seeds and coriander seeds. Poppy seeds are tiny and they will float. And I'm trying to write the word float on here in water. Okay, so the next thing would be to add water to this mixture. So put it in a beaker, add water. And coriander seeds are a little heavier, so they probably will sink. All right. And there is one thing in here that's soluble, right? Instead of coriander seeds, let's put, oh yeah, that's good. Let's just leave it like that. All right, so salt is going to dissolve. So this is going to be salt water now, right? Okay, so it's a mixture. They're all a mixture, but now we have another mixture because we added water to it. Okay, so since the poppy seeds float, we can catch them, we can fish them out. And one of the materials that I give you is little fish nets, you know, the ones that you use to transfer the fish from the tank out so that you can clean it, those. Okay, so they will float so you can fish them out. And then this one will sink. So if they sink, then you can use a coffee filter to get them off because the salt water will still be salt water. So then you can filter these out. So now you see all you have is salt water. And for this one, you can evaporate the water, right? Right here. You can heat and evaporate it. Evap. I'm just going to put evap because of it's kind of hard to write like this. Evaporate. I'm going to use my finger now. There. Okay. See. All right. So then you have your salt. And there you go. You have a whole separation. You have to think about all of this stuff. What would be the best order first? And all of that. Because, you know, if you don't follow the right order, then you might have a problem. And it's possible that the seed that you had these and these, you know, let's say that these and these were together in the sieve. All right, that's fine. Then you can just use tweezers to tweeze out the copper because the copper is very much obvious, right? Because of the color. So those are the properties that you're going to be using. So for this particular separation, and we're going to go over it again in class, but this is what you would need. You would need to know what your materials are, what the properties are of each one of your components, and which property of those components you can use to actually separate it from the mixture that you have with the materials that you are able to use. And that's it. That's all we have for today. We are done. And like I said, I will talk to you next time. Oh, Bobby, you're late.
I'm at practice, that's why.
Okay, I know you're late. And we're
Now?
just finished. Yeah, we're just finished.
Oh man, what I missed? Well, I'll just make it up whenever I go back to your class next week.
Yeah, and you can just I'm gonna repeat it anyway, this part, but not the other part. So you can just watch the video that I'm gonna post later. Okay.
Yes, ma'am. Thank you.
You're welcome. Bye bye.
You have a good one.
You too. Bye.
All right.
Bye.
Bye. So who's the iPhone that just walked in?
That was me.
No, not Kia's iPhone, the other iPhone.
That was Bobby.
That is Bobby? No, because Bobby said Bobby.
Oh no, I don't know.
So you notice how there's an iPhone
Let me see.
right next to you? Do you see it?
Yeah.
Okay.
I don't know who that is.
Can you write your name on the chat so I can count you in, please?
Huh?
This person, no, not you, the iPhone, the iPhone person that just walked in. Oh, they left. Okay, yeah, you. Can you please write your name on the chat, iPhone person? Because all it says is iPhone. I have no idea who you are. Oh, it's Ashley. Okay, thank you, ma'am. All right, so again, Ashley, since we just finished, you can watch the video afterwards when I post it, okay? All right. I will see you Monday. Take care. Bye-bye.